So this is the first of 3 introductory presentations where Claire and I will take you through all of the main features of the focused degradation kinetics guidance. So in the tour de table, I kind of gathered that quite a lot of you are very new to this area, which is good because we will really take you through all of the main features in a series of presentations, and then we'll link that to the hands-on workshops. This is just an outline of this first introductory part. So I'll start with a few words by way of introduction to the guidance itself, and then we'll start to get into some of the technical detail, and we'll look at the mathematical kinetic models that are recommended by the guidance. So starting with the simplest single first order kinetic model, and then moving on to the series of biphasic models that are recommended. Then we'll look at the tools for assessing goodness of fit. That's really important because one of the main jobs that we do when we do a kinetic assessment is try and fit one of those mathematical models to some of our experimental data. And we need some tools to decide if those fits are good or not. Then we'll combine those two things, the models and the goodness of fit criteria, and we'll look at some of the guidance on decision making. And in this first part, we'll be concentrating on parent substances. We'll look at metabolites in part 2 after lunch, and then we'll look at the specific issues around water sediment studies tomorrow morning. After I've taken you through some examples of decision making for selecting modelling endpoints and trigger endpoints, I'll hand over to Claire. And Claire will take you through the guidance on data handling, and then she'll introduce the concept of parameter optimization. And that will lead very nicely into our first hands-on exercise where you'll get the chance to build and fit first order and some biphasic models using a software tool called Model Maker. The way that we've tried to structure the training is really to give you as much time as possible working on a series of these hands-on exercises. That's not just because we want you to do all the hard work, it's because we think the best way for everyone to learn is learning by doing. And we also hope that by giving a group of regulators some quite complicated data sets, it's probably going to trigger quite a lot of discussion because we really want this to be an interactive workshop. I mean, I've been working on environmental fate since 1996, and I don't think a day goes by when I don't learn something new. So really everyone in the room has something to learn. So we'll try and get you as much time as possible on these hands-on exercises. But unfortunately, the focus kinetics guidance is quite a large document. Claire very kindly brought her copy with her, so it's over 400 pages long, and some of us have over a decade's worth of experience working with it. So there is quite a volume of information that we really want to get across to you in this series of presentations. So I apologise at the start that this is the longest presentation that you're going to have to sit through, but you can sit back and relax while me and Claire do the hard work, and afterwards you'll get a coffee. As I said, if there's anything that I say that you really don't understand, then by all means ask a question, but probably it will be easier if we pick up those questions once we get into the workshops. If you don't understand my voice or I'm speaking too quickly, then please also say. But if that's clear, we'll make a start with a few words by way of introduction to the guidance itself. I guess all of us realise that degradation kinetics is a pretty fundamental component of environmental risk assessment and hazard assessment. Key parameters like the DT50 can be extremely sensitive parameters in our environmental exposure models, and the biocide regulation includes some fairly straightforward hazard trigger-based endpoints based on DT50s, which can ultimately influence substance approval. So it's a fundamental part of our jobs. The original focus guidance came out in 2006, and there was an update, version 1.1 came out in 2014. That update was a fairly minor update to reflect changes that have gone on in the area of kinetics in other guidance documents. But it's worth noting that the guidance hasn't really been updated in a major way for over 10 years now. A really important thing to stress at the beginning of this workshop is that the guidance, of course, was written in the context of the pesticide legislation. Now, most of the basic principles are equally applicable to biocides or indeed the degradation of any type of chemical in the environment. But there are some parts that need a bit more thought. You need to be a little bit more careful when you're applying that guidance from the pesticide legislation to biocides. And of course, we also really need to seek working group agreement to harmonise the implementation of the focus guidance for biocides in these most difficult areas. And one of the jobs that we've set ourselves as an organising committee is to try and capture any of the key issues that are raised over the next few days, and then I guess we'll report back to the working group next year. I also have to say that this training course, sadly, is not a substitute for reading the guidance, all 436 pages of it, if you feel inclined, and even more importantly, gaining lots and lots of practical experience. We'll give you some of that experience over the next 2 days, but you really need to continue that when you get back to your home offices to really understand the guidance. The focus guidance follows the same kind of philosophy of all of the focus guidance documents, and that's really trying to standardize procedures, with one of the key goals being to try and remove the influence of the modeler and improve overall consistency in regulatory decision making. We have standardized study guidelines through the OECD guideline program, but they don't cover calculation of degradation rates. So the guidance is really extensive. It covers some quite simple things, things that we'll cover in our first workshop, so looking at first order kinetics just for parent compounds, and then it moves through to much more complex areas, looking at non-first order or biphasic kinetics, looking at multiple metabolite systems, complex degradation schemes, and water sediment studies. There's also some really good, clear guidance on things to improve consistency, like how you handle the data before you put it into your kinetic model, the standardized statistical and visual tests, as well as some decision flow charts to hopefully improve consistency. Although the guidance is really comprehensive, despite that, experience has shown that we still need considerable expertise to apply the recommendations to real-world data sets. So the influence of the user has not been completely removed. So for example, the user has to decide on the acceptability of visual fits. That's still quite a subjective part of the guidance. The user also has to decide on the appropriateness of endpoints for regulatory use. I think that's really important for us when we're working in the biocides area, remembering that the guidance was written under the pesticide scheme. The user, when you're using it for biocides, you have to think a little bit more carefully about whether the guidance is appropriate and whether the endpoints are appropriate for regulatory use under the biocides regulation. I should also acknowledge that many of the slides that I'm going to present have been adapted from some original training that was given by the focus work group back in 2005 or 2006. We've done quite a lot of work to update those slides, make them relevant for this particular event, and to update them in light of the experience that we've gained. But I am at least acknowledging at the start a certain amount of plagiarism of those slides. Okay. So we'll move on and start to get into some of the technical detail now with a look at the kinetic models that are recommended by the guidance. Focus workgroup did a couple of nice things actually in terms of the kinetic models. Firstly, they really constrained the number of kinetic models that are available to the user. Before the guidance came out, we would often see applicants applying a whole range of mathematical equations to fit to their degradation data. But Focus really constrained the number of models that are available. And they also tried to select kinetic models that had a physical basis, so that a model that could be used to describe a particular process as a chemical degrades in soil. And all of this section of the presentation is related to Chapter 5 of the guidance. And we'll start out looking at the simplest kinetic model, which is the single first order equation, and then we'll move through the sequence of biphasic kinetics. So thinking about first order kinetics, where does first order kinetics come from? Well, the first reason that Focus puts forward is one of experience. Experience shows us that many biotic and abiotic processes in the environment effectively follow single first order decay. We see this exponential decline as our substance degrades or dissipates in the environment. Second reason to think about first order reactions is one of pragmatism. The equation is really simple and it has only two parameters. It's easy to fit the equation to experimental data. Key endpoints like DT50s and DT90s, the time it takes for 50% or 90% of your chemical to degrade or dissipate, they're easy to calculate with this equation. And the parameters are theoretically independent of concentration and time. That makes them appropriate for use as input into our chemical fate models, particularly our chemical leaching models, things like focus groundwater, focus surface water. Those models are built on an assumption of single first order kinetics. So they can't handle degradation rates that are dependent on concentration or time. Okay. So for pragmatic reasons, SFO fits well with our models. And the final reason is scientific justification. Hydrolytic processes will often follow first order reaction kinetics, and biotic degradation processes may at least be approximated to first order reaction kinetics. For example, when the responsible microbial agents or the enzymes that are doing the degrading, when they're present far in excess compared to the concentration of the chemical, then at least it will simplify to a kind of pseudo first order reaction kinetics. If the responsible agents, the enzymes, were a rate limiting step in that reaction, then you might get a second order reaction. But very often our chemical is at a low concentration compared to the degrading media, if you like. And that brings us on to the first information box. And these information boxes you'll find in Chapter 5 of the guidance. And they're really useful because they contain pretty much all of the information that you need to be able to understand the different kinetic models and to start to build them into degradation schemes and into different bits of software. So I mentioned that the single first order kinetic model has two parameters, and you can see in the information box it tells you what the parameters to be determined are. So we have this M0 parameter. That's the total amount of chemical present at time 0. So it's the total mass in your system at the beginning. And then we have this parameter K, which is your first order rate constant. And in the yellow box on the right, we have some examples of how a substance will degrade or dissipate depending on those different K values, those different rate constants. So as the K value goes up, the degradation gets faster. As I said before, degradation is independent of time and initial concentration. So the fractional change is constant for any given time interval. So the time it takes for the first 50% of your substance to degrade is the same as it takes for the next 50% and the next 50%. So that fractional change is constant, determined by that K value parameter, that rate constant. And the rate constant is only dependent on the environment, so it could be dependent on temperature or soil moisture, for example. Within those information boxes, we also have the underlying differential equation. For the single first order kinetic, that differential equation is relatively simple, but it's useful to have it because many of the tools that we use in our kinetic fitting evaluations are able to solve sequences of differential equations. So if you know what the parameters are and you know what the differential equation is, you can start to build kinetic models to fit to some data. And that is absolutely what you will be doing in our first hands-on exercise. You'll be building kinetic models using these differential equations and these parameters. The information box also tells us how to calculate DT50s and DT90s, which are often very important outputs of our kinetic assessment. So single first order exponential decay, the DT50 is the natural log 2 divided by the rate constant. The DT90 is the natural log 10 divided by the rate constant. And because for the single first order kinetic, the fractional change is constant for any time interval, there is a constant relationship between your single first order DT90 and your single first order DT50. That relationship comes from the ratio of natural log 10 over log 2 and is a value of 3.32. I just mention it here because in about 45 minutes I will come back to that magic number, and I'm just putting there to make sure that you're all paying attention, okay? And if that was as complicated as Kinetics got, this could probably be a 2-hour training course rather than a 2-day training course. Because first order reaction kinetics are not always obeyed. So what reasons does the focus guidance put forward for why we might see non-first order reactions? Well, the first reason that focus says is heterogeneity or spatial variability. And that's the physical basis behind the first of our non-first order kinetic models, the first order multi-compartment or FOMC model. And FOMC assumes that your chemical degrades at different first order rate constants depending on its location. For example, its location in the soil environment. And the distribution of locations with those different rate constants follows a gamma distribution. A gamma distribution is just a type of probability density function described by 2 parameters, okay? And that results in quite a simply parameterized but time-dependent model. In terms of the physical basis, you can imagine that particular model describing degradation across a single field. So for example, where small changes in pH, organic carbon, biomass, etc., across that field will impact the degradation of your chemical on a micro scale. Your chemical won't degrade at exactly the same rate across the whole field because the environment is spatially variable. So your initial concentration or your initial mass is allocated to this continuous array of possible first order rate constants, those K values. That's described by this gamma distribution, and the FOMC model parameters describe both the shape of that distribution and the distribution or location of your substance. That's the physical basis for the FOMC model. And again, it brings us to one of the information boxes, which again contains really all the information that you need to understand and start to implement this model in one of the software packages. So again, it tells us what are the parameters that need to be determined. So again, we have that constant parameter, that M0 parameter, which, as I said before, is the total amount of chemical applied at the beginning of at time 0 at the beginning. And then we have these 2 new parameters, alpha and beta. Those are the 2 parameters that are used to describe the gamma distribution. Okay. And in the yellow box, we have some examples of FOMC model declines with just varying alpha and beta values. Just to remind you that constant relationship between DT90 and DT50 is only true for your single first order model. That's not true for any of the other models that we'll look at. The information box also gives us the differential equation, maybe starting to look a little bit more scary now, but if you have the software that can build and solve differential equations and you know what the model parameters are, then it's actually quite easy. And again, we'll do that in our first workshop. We'll build an FOMC model. Okay. Again, it tells you the equations for DT50 and DT90. So really, all the information that you need is there. Just to highlight that I will probably call it FOMC for the rest of the next 2 days. But if you read the focus guidance, then it is sometimes referred to as the Gustafsson and Holden model. They're just the two authors that first came up with this idea of describing spatial variability through this particular kinetic model. Just a slide on FOMC, just to reflect on some of the things that we've kind of learnt by experience after the guidance was written, okay? So although it's simple, and the FOMC model in the guidance is often put forward as the first biphasic model that you will test. Focus does that because it's the simplest biphasic model, and it says it's the simplest because it has just one extra parameter. FFO, single first order, has 2 parameters. FOMC has those 3 parameters. Okay, so it's kind of the simplest model. But although it is simple, it does have some quite significant drawbacks which limits its implementation. Okay, so FOMC cannot be directly implemented into our focus leaching models, so focus groundwater, focus surface water, because degradation is time dependent. Okay. We've also found that it can be quite difficult to optimize those 2 parameters, those alpha and beta parameters, to a unique solution. And you might come across that over the next couple of days when you start to try and fit this model. Sometimes it's hard to actually optimize those parameters. Also, the kind of conceptual model, or the physical basis of FOMC, is that it's a static model. And that's not really valid for dynamic environmental systems that we're dealing with. So if you think about a biocide that's released to soil via sludge or manure, that biocide will undergo dispersion, diffusion, mobility. So it's not a static system. And the FOMC model doesn't quite fit when you move into that kind of dynamic environment. We've also found that FOMC is not really suitable for accumulation, and it doesn't really work for repeat applications because you wouldn't expect those repeat applications to distribute to exactly the same identical compartments. And because the FOMC model is built on basically this continuous array of rate constants in these infinite number of compartments, some of those compartments will have 0 degradation rates associated with them. That makes extrapolation beyond the experimental period isn't really recommended. And the model tends to tail off towards infinity. So with the FOMC model, at least for some of those combinations of alpha and beta values, you'll find a fraction of your mass never degrades because some of those compartments have a 0 degradation rate. Okay, it doesn't really. It's hard to extrapolate beyond the experimental period, which is another drawback. So what about really the second reason for why we might see non-first order reactions? And the reason that focus puts forward is limited availability. So in soil, your chemical is distributed between the solid and liquid phases. And we often think that it's the liquid phase where they are most available for degradation. That's where they're going to come into contact with those responsible agents, the enzymes perhaps, that degrade it. And that pattern of partitioning can induce a biphasic pattern of degradation. So the available fraction in the liquid phase will decrease over time due to slow absorption and diffusion processes, and also because of nonlinear absorption. So when your Freundlich exponent, your 1/n value, is less than 1, what that means is it results in decreasing availability in the soil pore water with decreasing concentrations. Okay, so for many biocides, absorption is not linear; it's non-linear, which means as it degrades, the available fraction in the liquid phase decreases. Okay, and that pattern of partitioning can induce a biphasic pattern of degradation. The diagram on the right is the model of a kind of two-site absorption model, so you've got equilibrium absorption and non-equilibrium absorption. But that physical model of partitioning in soil can result in observations of biphasic degradation. Okay. And the physical model, or the kinetic model that Focus puts forward to describe that, is the double first order in parallel model, or DFOP. Probably the easiest way to understand this is to look at the top left. So what the DFOP model does is it basically divides your total mass into two compartments. And each of those compartments degrades with its own individual first order rate constant. Typically, we tend to think of compartment 1 being the fast degrading compartment and compartment 2 being the slower degrading compartment. The information box is a little bit more complicated than it really needs to be. There's two ways that you can describe it with two different sets of parameters. The more typical form is to use these four parameters. So again, M0, initial mass at time 0, is a constant parameter for all of the models. But now we have this G parameter. And the G parameter is just used to fraction up your total mass between those two compartments. Okay, so the G fraction is how much of the total is in compartment 1, and then 1 minus G is how much is in compartment 2. And then we have our two first order rate constants, K1 and K2, operating in parallel. Again, differential equation, starting to really look quite a bit scary now. But again, if you know what the parameters are and you know what the differential equation is, trust me, you can build it. And again, in the yellow box, we have some examples of different DFOP kinetic models with different K1 fast rate constants, K2 slow rate constants, and different proportions of mass in that compartment 1, that fast degrading compartment. An extra complication of the double first order in parallel model is that there is no simple analytical solution to calculating DT50s and DT90s. You have to calculate it iteratively from those equations on the info box. But the software tools that have been built do that for you. But it's just to point out that there isn't an analytical solution to DT50 and DT90. And this brings us to our final main model that's recommended by Focus, and that's the hockey stick model. Probably the easiest way to describe this is to look first at the yellow information box on the right. And basically the hockey stick model works by having a single first order rate constant for a certain time period until it reaches a breakpoint, and then the degradation switches to a different degradation rate. In the examples on the right, we have a fast rate constant up to the breakpoint and then a slower rate constant beyond the breakpoint. You can also do it the other way around. You can have a slow rate constant up to the breakpoint and then a faster rate constant after. And you could use that perhaps to describe maybe a lag phase where your substance isn't degrading for a certain period and then it starts to degrade. Again, we have the parameters to be determined, M0, K1, K2, just like DFOP. But rather than a G value for DFOP to fraction the mass between two compartments, we separate the two rate constants by this breakpoint, this TB parameter. And again, we have the DT50 and DT90 equations there. It's a little bit more difficult to think of the hockey stick model describing a real kind of physical process as a chemical degrades. Maybe for that lag phase where you've got no degradation up to the breakpoint and then degradation. Sometimes it can be quite useful in fitting whole system water sediment data. We'll come on to that tomorrow morning, but sometimes when you've got competing degradation and partitioning processes and you lump it all together as a whole system, the hockey stick model can be quite useful. And sometimes the hockey stick model can be useful for long-term outdoor field dissipation studies where you might have quite rapid or degradation over the summer period, and then as you move into the colder months, you get degradation slowing down. Okay. So that was the four mathematical models the main models that Focus recommends. And on this graphic, we have those 4 models, so single first order, FOMC, hockey stick, and DFOP, all on one graph. And in this example, the M0 parameter, which is common to all those 4 models, is common. It's 100% in each case, and in each case, they all have a DT50 of 5 days. The really important thing to remember is that the same DT50 does not mean the same pattern of decline when calculated using different kinetic models. So even though they all have the same DT50 and they all start with the same amount of mass, the same DT50 does not mean the same pattern. SFO and biphasic DT50s are also not interchangeable in our exposure models. So you cannot put an FOMC DT50 into one of our single first order based exposure models and expect the model to give you the same pattern of decline as your FOMC kinetic. Okay, so the exposure models are mostly limited to single first order. So don't put a non-first order DT50 into those models and expect it to work. Okay. Not only are they not interchangeable in the exposure models, they can't also be easily combined in averaging procedures. When we have quite large data sets and our guidance tells us that we should put an average degradation rate into our exposure model, it's also not that easy to average mixtures of SFO and biphasic kinetics. You can't average SFO DT50s and FOMC DT50s and DFOP DT50s and get anything that's particularly meaningful, okay? Not for modeling. So kind of basic, but probably keep coming back to that limitation, particularly when we're talking about exposure modeling. So just a summary on this first part. So for scientific and pragmatic reasons, Focus always recommends fitting the data to your single first order or SFO model. You always do that first. Because our fate models are typically, fate exposure models are typically limited to handling single first order kinetics, the Focus guidance acknowledges that there's kind of a desire to accept SFO for modeling endpoint selection, even when it's not the best fit. And often answering that question of when is my single first order fit good enough for modeling endpoint selection, that's often one of the most critical and difficult aspects of the kinetic evaluation that you'll do. And for sure, we will have some examples of those difficult decisions as we go through the various workshops. Just to acknowledge that the 2006 guidance and those decision flow schemes were written before the bespoke fitting tools were available. So the guidance was written before we had Cake or Kingui, for example. So now we have those tools. Kinetic fitting is so much more automated. Some of the simplifications that the Focus guidance tries to take you down, like it tries to prioritize FOMC as the simplest biphasic or non-SFO model. I would say that's a little bit less relevant now because it's so easy when you use software like Cake to fit all 4 models in sequence that kind of simplifying it is maybe not so relevant. And I'll come back to this last point later in this presentation, and we'll also pick it up after lunch when we talk about metabolites. But our experience has shown that there are quite a number of advantages of the DFOP model when it comes to selecting modeling endpoints that might outweigh the simplicity of just using the FOMC model as your first biphasic model. Okay. So we'll move on now and look at the tools that Focus recommends for assessing goodness of fit. And this is all the background to this is covered in Chapter 6. So the Focus work group tried really hard actually to try and identify a single, objective and universally valid statistical test that could be used for all kinetic models that could be easily and consistently applied. And to be honest, they failed. I feel a bit harsh saying they failed it when they produced such a great guidance document. They couldn't really find a single objective test that would work. So they ended up proposing three main tools: the visual assessment, the chi-squared statistic, and the t-test. And it's important to understand those three tools individually and also to understand how to use them collectively in your decision making. So don't use any single tool in isolation to accept or reject a fit. You have to use all the information that you get from those three tools in your decision making. And those tools can be used for assessing an individual goodness of fit. So when you've fitted just one of those kinetic models to your data, you can use these tools. And you can also use these tools to compare the goodness of fit of two different models. So sometimes you run two different models and you want to use the tools to compare between those models. And on this presentation, this part of the presentation, we'll just take you through each of those three main tools in turn. So we start with what I would say is the main tool, really, the visual assessment. And although it's subjective, because it's really up to you as the kinetic modeler to make that decision based on the visual assessment, it is a really powerful tool for assessing goodness of fit. And it keeps common sense in the assessment process, and that common sense might have been lost if we just relied on statistical tests. Okay? Focus recommends two different plots to perform the visual assessment. There's a typical plot, which is on the top right, and that's just a plot of your fitted model versus your observed residues over time. Okay, so the line is your model, the black dots are your experimental data. The second recommended plot on the bottom right is the plot of residuals, and that's just your predicted model minus your observed residues at each time point. Okay, and obviously better visual fits will be seen when your model most closely matches your observed data, but better fitting models will typically show smaller residues, and those residues, when you look at the residual plot, they will be randomly distributed over the course of time. If you see large and systematic patterns in your residuals, then that can indicate a poorer fit. When you're looking at the typical plot, there are things that you look for. You look to see, have you described the initial concentration well or not? So that kind of, have you described the M0 parameter? Or does your M0 parameter accurately describe the actual initial concentration in your test system? And here on the top right, you can see actually that the model doesn't really do a very good job of describing the initial mass. The residues are, there's an error on your residues there of more than 10%. You can also look to see on your typical plot whether you get a good description around your expected DT50 and your DT90. Over time you'll get more experienced with this, but I would say on that example, actually the fit of your model to the DT50 isn't too bad, okay? But the fit to the DT90 is really, really bad because our experimental data, we still have nearly 20% remaining at the end of that study. So we haven't reached the DT90. The DT90 is the time when you only have 10% of your initial mass remaining. So in our experiment, we've not reached the DT90, but our fitted model tells us that the DT90 is reached after about 60 days. So actually a really poor fit to the DT90. And that is kind of reflected also in the residual plot, where you see a systematic pattern in the residuals, and when you start to see 3, 4 residuals consistently on one side of the axis there, you kind of know that your model is starting to systematically deviate from your experimental data. Okay? Next tool is the chi-squared statistic, and this considers the deviations between your observed and calculated values relative to the uncertainty of the measurements. Okay? Now, in the kinds of experiments that we deal with, the measurement error is typically unknown. We'd have to repeat those water sediment studies or those lab soil degradation studies lots and lots of times to be able to quantify the measurement error. But we never really do that. So what Focus did, the Focus work group proposed a common error model. So the percent error is scaled to the mean of the observed values. That means that the relative error, because it's based on the mean of the observed values, the relative error is lower for the early time points, where you've got a lot of mass, and the relative error increases for later time points, where you've got lower concentrations. And that's just consistent with another of the Focus work group recommendations, which was to use unweighted fits. And we'll come on to weighting and unweighted fits towards the end of this presentation. You don't really need to understand the chi-squared statistic, but I like to kind of give you the basis for it. The really important thing is that with this statistical test, the minimum error percentage at which the test is passed can be directly calculated. Okay, so that's what the chi-squared test does. It calculates the minimum error percentage at which the test is passed at a certain significance level. And models with lower chi-squared error percentages are better fits. Okay. The Focus guidance envisaged really two roles for the chi-squared error percentage test. The first was to discriminate between different kinetic model fits. So when you're looking at, say, single first order and a biphasic model, the chi-squared statistic can be quite useful to discriminate between those two. And the model with the lower chi-squared error percentage is the better one, in simple terms. Focus also thought that the chi-squared test would be useful to support decision-making on whether an individual fit is acceptable by kind of supplementing the visual assessment. So your visual assessment is still the main tool, but it can be supplemented by this chi-squared statistic. However, an important point to point out is that the chi-squared error percentage doesn't differentiate between systematic and non-systematic deviations. And it's those systematic deviations that you can really pick up very easily with the visual assessment. But the chi-squared statistic doesn't really do that. Okay. So when you look by eye, you can see that your model is systematically starting to deviate from your observed data. But chi-squared doesn't do that. So sometimes you can get large chi-squared error percentages just as a result of data scatter around a fitted line. So sometimes your model can actually be quite a good fit to the data, but if it's very scattered data, you'll get a high chi-squared statistic. So that's where you need the visual assessment, which brings that kind of common sense into the process, into the decision-making process. Chi-squareds above 15% might indicate that the fit's not adequate, but the intention of the original group was not to use that test as a strict cutoff in decision-making. So when it mentions 15%, it's kind of an indicative value to indicate below 15%, it might be acceptable. Above 15%, it might not be. But don't use it in isolation. Use all three tools together. Because we have these bespoke tools like Cake that you'll be playing with this afternoon, the chi-squared error percentage is calculated as standard by that software. And the chi-squared, it takes into account the degrees of freedom and the significance level. We're normally looking at a 5% significance level, and the degrees of freedom here is simply calculated as the number of data points minus the number of fitted parameters. So when we went through those information boxes earlier, and I said SFO has 2 parameters, FOMC has 3, and DFOP and hockey stick have 4, that has an implication because it determines the number of degrees of freedom in the chi-squared statistic. So when you're using the chi-squared to discriminate between different models, you need to look at the magnitude, the size of difference, and not just the absolute value. And one reason that is important is if you are comparing DFOP and FOMC and they give exactly the same chi-squared error percentage, the DFOP model might actually fit better because it has less degrees of freedom because it has one more parameter than FOMC. Okay, so think about the magnitude and not just the absolute value. So when I said before the model with the lower chi-squared is the better one, that's true, but you also need to think about how the number of fitted parameters can influence that. Okay, large differences, it's clear that one model is better than the other. But if the differences are small or the values are almost equal, you might need to think about looking at the visual assessment as well as just using the absolute chi-squared value. Last tool is the t-test, and Focus recommended the t-test as a means to assess whether or not a parameter is significantly different from zero. So Focus says if your p-value from your t-test, which is calculated as standard by things like cake, so don't worry too much about the maths, if p is less than 0.05, then your parameter is considered significantly different from zero. Technically, the t-test is only applicable to degradation rate constants, so those k values of FFO, DFOP, and hockey stick models. You shouldn't really use it for other parameters, so don't use it for alpha and beta of FOMC, don't use it for the g value of DFOP. It's only really applicable to rate constants. And it's important to stress that the t-test does not indicate parameter reliability. It merely checks if the parameter is different from zero. Okay? So don't think that a passed t-test means that your parameter is reliable. It just means that it's different from zero. It just means that the level of uncertainty is low. And another really important point that I would stress to you is that data sets should not be rejected based on the outcome of the t-test alone. One thing that we've learned through experience is that many kinetic modelers will reject a whole study because it fails the t-test. That particularly comes when we see kinetic reports produced by applicants. Okay, and the reason I say don't reject it based on the t-test is because if you have, say, a large number of studies, say you've studied degradation in 4 soils, the soils where degradation is slowest will be the ones that are most likely to fail the t-test, okay, because that's where degradation rate is lowest. They'll be most likely to fail the t-test. So if you reject the soils where the t-test is failed, effectively you're biasing your selection in favour of the soils or the studies where degradation is faster. And you're actually throwing out information from studies or soils where the substance was persistent. And of course, if we're interested in doing environmental modelling or looking at hazard assessments, we're actually worried about the situations where the substance is persistent. Yeah. So don't misuse the t-test to completely reject a study when it fails. And we'll look at some examples of how you can get around that and what you do later. Sometimes with the t-test, the fast K1 parameter of the DFOP model can fail. And you sometimes see that for really quickly degrading substances. You know, we have some biocides, some disinfectants that actually degrade incredibly quickly. And sometimes, statistically, the t-test can fail on that fast K1 rate constant because degradation is so fast that there isn't enough data to statistically show that it's different from zero. But in those situations, it's a little bit illogical to use the t-test to reject the K1 parameter. It's just so rapidly degrading that you haven't got enough data to describe it. So don't use the t-test in that kind of scenario as well to be too worried about a fast rate constant. Perhaps more commonly, you'll see the t-test fail for the slow K2 rate constants of either the hockey stick model or the DFOP model. And that's when degradation is very slow and it's extrapolated beyond the study duration. Okay. The t-test can be really useful for assessing metabolites without a clear decline phase, and we'll talk about that in a bit more detail this afternoon. When the p-value of your t-test is between 0.05 and 0.1, Focus recommends using a weight of evidence approach. That could mean looking to see if there's evidence from other studies or other soils that would support the long DT50 that you've got in the soil that you're currently considering. And as I said, rather than just reject data sets that indicate persistence, those fitted values that are uncertain, as shown by the t-test, can be replaced with default values. The standard Focus default is 1,000 days. and you can recheck the fit, and we'll maybe have a look at that in some of the workshops later. Okay, so this is the last section that I'm going to take you through. And it kind of combines the kinetic models and the goodness of fit criteria to look at some decision-making guidance. And as I said at the beginning, we'll just look at parent substances in this section. We'll move on and look at metabolites after lunch. So we'll look at decision-making when you want to select a trigger or a persistence endpoint, as well as the decision-making that you would undergo when you're looking to select an exposure modeling endpoint. And for parent substances, all this guidance comes in Chapter 7 of Focus. But first, a few words just to say, why is there a distinction between the kinetic fitting that you would do when you want to identify a trigger endpoint or a persistence endpoint versus the decision-making that you would make when selecting an exposure modeling endpoint? Well, regulatory triggers are based on DT50 and DT90 values that are not constrained to any kinetic model form. So the model that most appropriately describes the observed data should be used to generate those trigger endpoints. So you want the best fit, okay? Not constrained to any kinetic model. Just to give you a couple of examples, Volume 4, Part A, information requirements for biocides. The triggers for field dissipation studies are based on DT50 and DT90 triggers. The reason that we have those DT50 and DT90 triggers is that you can then compare any kinetic model to them, okay? So you don't just need an FFO model, you can compare biphasic models to those triggers. That's why it has a DT90 trigger in there, okay? If you look at REACH R11, guidance for our PBT assessments, again, REACH guidance talks about what you would do when you have to consider non-single first order or biphasic models. So again, those trigger assessments are not constrained to any kinetic model. In contrast, our current regulatory environmental exposure models are almost always based on an assumption of single first order kinetics. So if you look at EUCs, the ECHA spreadsheets that our friends at the back have spent so much time developing, the focus models, they're all based on that assumption of single first order kinetics. So an endpoint, like a DT50, calculated using a non-single first order kinetic will not appropriately represent the observed behavior when you put it into an SFO-based exposure model. So think back to that graphic of the four kinetic models on one. So in that situation, you need to use either an SFO endpoint, if it's appropriate, if the SFO fit is good enough, or you need to use a conservative estimate or a workaround to be able to implement a biphasic kinetic into an SFO-based exposure model. And that concept of conservative estimates or workarounds is a really important part of how focus guidance gets around the problem of our limited exposure models based on single first order kinetics. Within Chapter 7, there's some really detailed decision flowcharts, but they don't really lend themselves to presentations. You have to zoom in and zoom out to see all the different elements, which is beyond my technical capabilities. So I have summarized those decision flowcharts simply on this slide. And on the left, we have the decision flowchart that you would go through for selecting a trigger or persistence endpoints. And on the right, we have the kind of flow for selecting modeling endpoints. And I'll take you through the trigger endpoint first. There are some things that are common between the two, so you will eliminate any obvious artifacts or procedural errors prior to conducting your kinetic analysis. Claire might pick up some of those points in the next section on data handling. But when you're making your decision on selecting a trigger or persistence endpoint, Focus says your first task is to run SFO and FOMC as a first step. And then you check the visual fit, chi-squared, and do the t-test. Focus allows you to go through a kind of an iterative loop where you could modify your fitting routine in a stepwise way. You might exclude outliers, you might constrain certain parameters, you might weight the data, for example. But ultimately, if FOMC is shown to be better than SFO, then you test the DFOP model. And ultimately, at the end, you pick your best fit model, and you use those best fit model endpoints like DT50 and DT90 against your regulatory triggers, whether it's triggers for triggering field dissipation studies or your the persistence assessment of your PBT part of your substance evaluation. Okay. For modeling endpoints, remember that focus is kind of acknowledging that our exposure models are SFO based. So there's a kind of a desire to accept SFO if it's good enough. Okay. So when you're going down the modeling endpoint selection route, focus says you run SFO as a first step. Again, check visual fit, chi-squared, t-test, go through this modified fitting routine, excluding outliers if you need to. If the visual fit is acceptable, if the SFO fit is good enough, if your chi-squared error percentage is less than that indicative value of 15%, and your parameter is significantly different from 0 according to the t-test, then happy days. You can use your single first order DT50 in your exposure model. If your visual fit's unacceptable, chi-squared error is greater than 15%, then you need to run a biphasic model, okay? Because you've basically decided that your SFO fit isn't good enough. And then the focus decision flow chart says there's a decision to make based on how much mass you have at the end of the study. If 10% of the initial is reached within the study period, so if you've reached the DT90 within your experimental period, then the workaround, the conservative workaround that Focus recommends is that you take your FOMC DT90 divided by 3.32. I told you that would come back, and there it is. So you've stayed awake. Well done. If 10% of the initial mass is not reached within the study period, then you use the DT50 from the slow phase, so that K2 rate constant from either DFOP or hockey stick. Again, both of those two bullet points are those conservative workarounds, okay? So ultimately, at the end of that process, you'll either use your SFO fit, if it's good enough, or you'll use one of those biphasic workarounds for a parent substance only, okay? Just to explain the FOMC DT90 divided by 3.32 concept as a modeling workaround. So what we have here is the fitted model in blue and the workaround, the DT90 divided by 3.32 in red, okay? And that FOMC DT90 divided by 3.3 workaround provides a conservative estimate of your residue decline up to the DT90. So because the red line is above your data points up to the DT90, it's conservative up to that point, okay? Remember that the conservatism of those workarounds is only true for parent-only modeling exposure assessments, okay? Because the impact of those workaround conservative DT50s on subsequent metabolites is a bit unknown, okay? So if you put a conservative parent DT50 into an exposure model like focused groundwater that sequentially forms metabolites, then slowing down the parent degradation rate is only conservative for the parent. It might actually be less conservative for the metabolite. That's a bit of a limitation of these workarounds, and we'll come back to that after lunch when we talk about metabolites. So just remember, these conservative workarounds, whether it's K2 rate constant or FOMC DT90 divided by 3.32, should really only be used when you've got a parent-only exposure assessment. Okay, so let's look at an example. Firstly, thinking about how you would select a trigger endpoint from some real data. And here we have just an example of some experimental data. It's 120-day data. We've got replicate time points. It could be a soil degradation study. It could be a water sediment study, for example. One important thing to note is that the focus kinetics guidance treats the formation of non-extractable residues as a dissipation process. And subsequently, it excludes those NERs from the subsequent fitting. You need to be aware, if you're not already aware, that there are differences with the REACH R11 guidance, and Jan will take us through that tomorrow afternoon. But for the rest of this presentation and for the rest of the workshop, we are really presenting what Focus Kinetic tells you about how to do the kinetics. So Focus says we'll treat the formation of NER as a dissipation process and we'll remove it from the equation. So this is just some experimental data of extractable chemical. Okay. So remembering we're looking at the trigger decision scheme first, and Focus says you run SFO and FOMC as a first step. Okay, so on the left we've got our SFO fit, and on the right we've got our FOMC fit. I said that Focus talks about using the chi-squared to discriminate between two model fits, and you can see that your SFO fit gives you a chi-squared of 19, your FOMC gives you a chi-squared of 7, so quite a big difference. So even without looking at the visual fits, I would be thinking my FOMC fit is probably better than my SFO fit. And when you start to look at the visual fit, you can see that that's true. We have a relatively poor fit to our SFO model. Systematic deviations, your model is systematically deviating from your experimental data. Your FOMC fit is a lot better. There's a lot closer match between your experimental model, your kinetic model, and your experimental data. And the residues are smaller and more evenly scattered. Okay. So the decision scheme says FOMC is better than SFO, so run DFOP. So here we have the same FOMC fit on the left now, but our new DFOP fit on the right. Again, just looking at the chi-squared error, with DFOP we get a chi-squared error percentage of 1 compared to 7. So again, it's kind of telling us that maybe DFOP's better than FOMC. And looking visually, I think you could probably quite easily tell, even if you've never done this before, that your DFOP fit is better. You're getting a much closer match on the typical plot to the experimental data, and again, smaller and more evenly scattered residues, even in the FOMC model. Okay. But let's not forget our t-test, our test of parameter uncertainty. So the t-test results are on the final column on the right. Just worth pointing out that here the t-test for our SFO rate constant actually passes. So when I said the t-test doesn't tell you if your parameter is reliable or not, that's an example of it, because it's passed the t-test, but actually we've rejected it because it was a poor visual fit and the chi-squared was quite high. Don't do the t-test for FOMC, do the t-test for those rate constants, okay? And K1 rate constant, the fast phase rate constant, not surprisingly passes because it's a high number. The K2, the slow rate constant, it fails. It fails the t-test. Your p-value is not less than 0.05, it's not less than 0.1, it's 0.229 here. So we failed our t-test on the K2 rate constant. So what are some possible conclusions for this data set for selection of trigger endpoints or persistence endpoints? Well, the DFOP fit provided the best visual fit, and that was supported by the chi-squared test used to compare different models. But the t-test indicated that K2 was not significantly different from 0, so that parameter is uncertain. As I said, don't reject that completely based on the t-test, because that could impact on regulatory decision making. In this example, our FOMC DT90 is 160 days. Our DFOP fit gives us a DT90 of 472 days. So remembering that FOMC DT90 was 160 days, that would actually impact our regulatory decision making if we were thinking about whether that information would trigger us the need to conduct a field dissipation study. Volume 4 Part A has a DT90 trigger of 200 days. Also, we'd be concerned about accumulation in soil, for example, if the DT90 was greater than a year. So if we'd rejected that DFOP fit completely, we might actually come to a different regulatory decision, which would be perhaps a misuse maybe of the t-test. So there are several options exist. We could just use the DFOP with the fitted endpoints. We could accept those fitted endpoints and relax the t-test criteria based on a really excellent visual fit and a very, very low chi-squared. It would always be good to use a kind of weight of evidence approach to support that decision. You could check to see if there's other information from other studies that would support that long DT90 of 472 days. Alternatively, you can fix the K2 rate constant to a conservative value. Focus says 1,000 days is conservative, and you can recheck the fit. It's easier to show you that kind of thing in some of the workshops later. But if you do fix that K2 rate constant to 1,000 days, actually the chi-squared and the visual fit looks almost identical. The DT50 stays the same almost, and the DT90 increases to 922 days in that case. But for comparison with the regulatory triggers, the result is actually the same. Okay, so one important thing to think about when you're looking at trigger or persistence endpoints is what's the context. If you've got a study where your DT90 is obviously really, really long, then you've got a persistent substance that's probably going to breach your persistence trigger. So think about the context as well as the absolute numbers or the focus rules that you're applying. Okay. Keep it simple. We'll look at the same data, but we'll look at now at selecting modeling endpoints. Okay. So the focus flowchart says you run your single first order fit as a first step. We've already seen this fit from the trigger endpoints, but just to reiterate, the visual fit is pretty poor, chi-squared greater than 15%, and as a kinetic assessor, I would come to the conclusion that my SFO fit is not good enough for modelling. Okay, I'm going to not describe the decline of my substance if I use that kinetic model in my exposure model. In this case, 10% of the initial is not reached within the study period. Okay, so we can't use that FOMC DT90 workaround because of that limitation on the FOMC model. You can't extrapolate FOMC beyond your experimental period. Okay, so we need to use the DT50 from the slow phase, from the K2 of DFOP or hockey stick. We saw DFOP in the trigger decision. The only new fit on this slide is our hockey stick fit. Slight difference in the chi-squared. Chi-squared slightly higher for hockey stick. Bit difficult to tell if there's much of a difference between the visual fit, but I would say maybe the hockey stick fit is a little bit worse than DFOP if you just look at the residuals and that typical plot, but it's a bit difficult to see. I've put on here the individual DT50s based on the K1 and K2 rate constants. Okay, so the second DT50 values on this slide are the DT50s that you would get from the slow phase K2 rate constants. Okay. Again, we have to do the t-test. We know that the DFOP K2 fails because we did that in the trigger decision a few slides ago. But here, the hockey stick K1 and K2 both pass the t-test. Okay, so they're both shown to be statistically different from 0. So what are some possible conclusions from this data set when we're selecting modelling endpoints? Well, DFOP and hockey stick provide good visual fit, both with low chi-squareds, but the t-test indicates that your K2 of DFOP is not significantly different from 0. So that parameter is uncertain. So there are several options exist. We could use the slow phase K2 rate constant of the hockey stick model to derive a conservative DT50 for parent-only modelling. Your hockey stick K2 rate constant is there, and that's equivalent to a DT50 of 175 days. Okay. Another option would be to refit your DFOP fit with a K2 value fixed to 1,000 days, and that would mean using 1,000 days in your exposure model. Now you might ask yourself, if you were an applicant with an interest in actually getting your substance to pass the Biocides environmental risk assessment, if I had a choice between 175 days or 1,000 days, why would I pick 1,000 days? Okay. But there are some advantages of DFOP kinetics for exposure modelling. Okay. So those DFOP parameters like K1, K2, and G, they can be combined with single first order rate constants to derive average input values that can be suitable for use in exposure models. So many of our Biocides ESDs and the focus models, you can derive average values that you can use. And although I've said numerous times that our exposure models are limited to single first order kinetics, it is actually possible to implement DFOP fits in our emission scenario document calculations or the focus model. That is possible. It requires you to perform 2 separate modelling runs, but remember the DFOP fit, all it does is it separates out your mass into a fast degrading compartment and a slow degrading compartment. So you can actually run a DFOP kinetic in one of the ECHA Excel calculators if you want. It just requires you to run the model first for your fast phase, then run it again for your slow phase, and add up the 2 concentrations. And that can offer quite a significant refinement over those simple workarounds where you're using either 1,000 days or 175 days, okay? Because actually for that DFOP fit, there was quite a lot of mass in that fast degrading compartment. About 80% of the mass was in the fast compartment, which degraded with a half-life of about 7 days. So for an exposure model, it might actually be better to use DFOP. There's one extra complication when we deal with some of our more complex mechanistic models, like the focused groundwater models, when they introduce the concept of non-linear absorption through that Freundlich exponent. When your Freundlich 1/n value isn't 1 and absorption is non-linear, then there's a little bit of an error introduced when you separate out the mass because absorption is concentration dependent. So focus gets around that by doubling the application rate, taking the answer from your focus model and then dividing it by 2 before adding it together. But perhaps not something you're going to do very often, but I just mention it as an extra complication of mechanistic models when you try and implement DFOP. But where the option exists, the advantages of the DFOP model might make it sensible to select DFOP fit into modelling. Okay, and we'll come back and touch on that again when we talk about metabolites. And you and I will be greatly relieved that that is it from me for now until after lunch, and I will hand over to Claire, who will take you through the last 2 sections. Is everyone okay to carry on? There's just 2 more sections. Claire, maybe 20 minutes. Is it?
15 minutes, and then questions at the end.
Yeah. I think Jan's been baking cakes all night for us. You'll get your reward, please.
Okay, so as James mentioned at the start, there's quite a lot to get through. So if you have any questions that you really just don't get what I'm saying, just raise your hand and I'll come to you. I'm actually from Scotland in the UK, and our accents are even faster than normal Britons. So if I'm going too fast, I'm sure James will wave at me at the back to say slow down. But I am aware of it, so don't feel bad if you don't understand what I'm saying. It is my accent. So on this session, I'm going to be looking at data handling, as James has already mentioned. So I'm going to explain the general recommendations, what you need to do before you start your kinetic model, because it's very easy to get your data set, put it in Excel, and just run the software. You don't actually need to understand focused kinetics to run the software and get an answer. What's really important is that you understand if that answer is appropriate or not. To improve consistency between evaluators, we follow standardized data handling processes. A bit too short for this. So the first thing we look at is data quality, and it's something you really should never forget to do. So the data must provide a sufficient and adequate number of sampling points to ensure a robust estimation as possible. But what does that mean? So the number of data points should be greater than the numbers of parameters considered within your kinetic model. And I've realized we're seeing this quite a lot. So for single first order, there's 2. So that's your M0 or your K value. In the practicals, I call M0 TA. They mean the same thing, but I'll mention it now before you open your practicals and realize I've used a different terminology. So FOMC you have three. So your initial concentration, alpha and beta, and for DFOP and hockey stick, you have 4 each. That would be your initial concentration, K1, K2, and G for DFOP, and TB, or your breakpoint for hockey stick. So 2, 3, 4, 4, 40 numbers to remember for your parameters. So theoretically, the minimum you need is 1 data point more than your parameter of your selected kinetic models. So if you want to go through the whole decision-making chart, theoretically, you need a minimum of 5 data points. And that's theoretically, and in practice, you normally do need quite a bit more. So it's worth noting, for example, the OECD guideline on cell degradation indicates 6 data points should be taken as a minimum, and the CTAC guidance has 8. So the guidance that you're using to create the studies indicates more than the kinetic minimum, theoretically. And I do stress theoretically. And we generally see the better the quality of the data, the smaller number of data points that are needed. So if you have a clear decline curve, such as this, you may not need as many data points as a curve that didn't quite show a clear decline phase. So for example, if you had a bit more scatter and maybe randomized pattern above and below, you might need some more data points. So for parent substances, it's important that the data you have show a clear decline phase. For metabolites and parents and sediments, so in water sediment studies, you apply the substance to the water phase and it will partition into the sediment phase. So for sediments and metabolites, you also have a formation of the substance in sediments or formation of the metabolite and a plateau phase, and James will explain what a plateau phase is later on today. But we've already mentioned rapidly degrading substances, and again, these are treated a little bit differently. It simply might not be feasible to collect enough samples before your DT50 is reached. If your DT50 is less than 1 day, we often see people taking sampling at time 0, 0.25 days, 0.5 days, and 1 day, and sometimes they still can't capture the DT50 because it's so rapid. In these instances, we wouldn't reject the data simply because there's not enough data points. What we would do, only for rapidly degrading substances, is we would follow the normal focus kinetic rules, and if we could find an acceptable fit, we would make use of that DT50. From a practical point of view, in the past, what I've done is I've had data where the DT50 was less than 1 day, but I only had day 0 values and day 1 0. So you couldn't really tell where in that 1 day the DT50 would lie. So what I concluded was, in my risk assessment, I was going to use 1 day as a conservative estimate because we couldn't reliably indicate with the data we had where the DT50 would lie between 0 and 1 day. Obviously, if you had more data points, you might not need that workaround. But with QSARs, you normally have a good idea what your DT50 value of your substance could be, and we'd expect the sampling regime to match that. So most studies can be conducted using either single or multiple replicates at each sampling point. True replicates should be used individually in your kinetic assessment. And by true replicates, I mean in the labs when you've got your individual flasks, or out in the field where you're taking soil cores from different locations. Any analytical replicates, so this could be where you've tested the same flask 2 or 3 times, or you've run a sample through the HPLC or whatever machine you have multiple times. We would average those values for use within the kinetic assessment. As James has mentioned, we would use, in the chi-squared calculations, we would average the replicate values for use within that statistical test. Remember, the software they'll use today will calculate it for you, so you don't have to understand this 100%. but this ensures that the chi-squared is measuring the goodness of the kinetic model and not measuring the replicates that you have to the scatter. So your chi-squared is a reflection of the kinetic model, not the variation in your replicate values. I'll point this out now, and we're going to come back to this tomorrow. So this is just to introduce the concept. When you have a study which has used different radiolabel positions, you have to take a bit of care. For parent substances, you can use them as true replicates. So model your data using all the data available. However, it's a bit more complicated for metabolites, as you can have parents going into 2 metabolites and it could be 1 mole to 1 mole. And when we come to the mass calculations that James will explain this afternoon, it can become more complicated. So at the moment, I expect you to get about 5% of that. So take-home message, parent data, you can run it together. Metabolites, some care needs to be taken, and we'll explain that more. We'll introduce it this afternoon, and in one of the practical sessions tomorrow, that issue does come up, and we'll have a wider discussion then. But I just wanted to highlight it as part of this evaluation. Also mentioned before was experimental artifacts. So the decision-making process, we have instructions to discard results clearly arising from analytical or procedural errors before analysis. So the focus kinetic guidance gave some examples of artifacts that may occur, what information sources you could look at to identify whether these are artifacts or not, and provide a recommendation of how to handle that as you're conducting your kinetic evaluation. But they didn't have all the answers, and some of it is still case-by-case decision. For example, if you observed a soil pH shift within the study period, you would look at the measurements of the pH to identify that. But the impact of pH altering will differ substance to substance. So you may have a substance which is not, the degradation is not independent to pH, so it's pH-dependent degradation. You may need to look at other studies that you have to identify that. You might not necessarily know if it's single soil in one study. So it's very case by case exactly how you would treat this in your kinetic data sets. But this is done before you go anywhere near the software, so we're still in the evaluation stage. Also can get outliers. Sometimes it's really easy to identify outliers. Maybe at a certain time point you might get 200% of your applied radioactivity, and it's quite clear something's gone wrong within the sampling. But more commonly, you may get a decline phase where perhaps you've got a slight increase at one of the time points. Now, with regards to perceived outliers, before you did anything to the kinetic data set, you would run kinetic analysis on all the data, including any data points where you think it's an outlier. Whether the analysis is repeated, removing your outlier is based upon expert judgment. There's not one rule that will let you identify whether your data point is an outlier or not. Because we work in environmental data, you accept a certain amount of scatter in natural data. So if you had a perfect line, you might be in a chemistry evaluation. Environmental data, you get more scatter. So kinetic fittings don't always follow this line straight down. So some evaluators will use statistical tests to identify the outliers. This will alter evaluator to evaluator, as it's currently not a harmonized area, but it's really important to note that the focus guidance indicates that if you have a limited amount of data, it might not be appropriate to use any statistical test to identify an outlier. So, we've mentioned before, the kinetic guidance is quite large, and it is worth reading for small bits of information such as this, where you've got to take a step back and think about the data set you have and not apply a statistical test without thinking about what that statistical test is looking for and potential limitations of the statistical test. So we have an example here where we've ran it initially with the outlier and got a DT50 of 42 days. This looks to be single first order. And then we excluded the outlier, and it's 34 days. So we've had a decrease by removing this outlier. Now, this is real data. Show of hands, who would remove this data point, kind of, if they've seen this in a study? Who would say, oh, that's definitely something wrong with the study? Anyone? Don't know. James is going to take it out. Anyone else? Any other?
Based on what? Well, I would be looking to see if there was a reason behind that.
Yeah.
The mass balance, the real data.
Yeah.
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 Probably, to be honest, when you look at the outlier, you'd rather have 2 or 3 more data points after the outlier.
Yeah. And I think it brings the important point that you wouldn't look at the graph in isolation. You would look at the study as a whole. So before you start your kinetic analysis, you've already concluded that your study is valid according to the guidelines and/or regulation. So at this point, we go back and look at, for example, if it was sacrificial sampling, are we confident in the dosing or other issues? The study is valid, but is there a reason in the study write-up that would explain this or not? And it's quite a common discussion that we've had on repeat about when is an outlier appropriate to remove or not. So we don't have the answers, and it is discussion with colleagues. So actually having a forum with you all here is really useful. And so hopefully as we do the practical, this type of discussion can start to go between us and we get an idea of what other people's opinions are. Because when you're writing it up, it can be really useful to know, oh, when I did the kinetic training, I remembered someone was concerned about what the percentage is about degradation. And you can include that in your write-up, which can be helpful at commenting to reduce your comments. So it's very careful and important that we treat our time zero samples in a slightly different way. So in most studies, you apply a defined amount of parent to a test vessel. This is a known concentration. However, there's often a delay between you applying the chemical to your vessel and you taking the first phase zero sample. And this can be half a day to potentially half an hour to 2 hours, I should say. And this can lead to metabolites or bound residues forming. As this is an artifact of your delayed sampling times, when we do kinetic analysis, any mass that has been detected as a parent or extracted residue, non-extracted residue, we assign to the parent mass. So bound residue, metabolites, we set to zero concentration, and any mass that's been associated with them, we assign to the parent. This principle also applies to water sediment systems, where we'll assign all the initial mass to parent and water. But James will come back to that tomorrow morning. So when you're conducting your kinetic evaluation, we use initial concentration as one of the parameter variables, and we would always run this freely. However, if you're having difficulty getting a fit, or your model is producing initial values that seem inappropriate compared to your measured value, you may wish to fix the initial concentration or constrain the initial concentration. So in this example, the soil residue is about 0.16, that's the measured value, while when it was optimizing, it got about 0.13. So a decision was taken to fix the value to the measured value. So as you can see, this has some impact on the resulting fit in terms of shape and also the DT50. So by fixing it, the DT50 is now shorter. You can also constrain this. So I can tell the software, I want you to parameterize, optimize the parameter, but you can only have a value between 0.15 and 0.8. And it will...
Which one is the corrected one?
Pardon?
Which one is the one you have corrected?
So M0 fixed is the blue line. So this is when we've told the software, do not optimize the initial concentration. In your SFO, it must be M0 must be 0.16, for an example. So the model is only looking to change K value to find a good fit. I'll explain optimization in a couple of slides' time, and it will make more sense. But it's just worth noting that there is an option to fix the parent and also restrict it. As James mentioned, we can also weight the data, but as a first step, we should always use unweighted data. And the weighted data should be used to reflect the uncertainty associated with each of the time points and should not be performed merely to change the fit. So for example, as is here, you could log transform the data, or you could take a 90th percentile of replicate values. The impact of weighting data will be case by case. So we've got two examples on the screen. In the first example, when we have log transformed the data, see there's been a change of 6 days in the DT50. So not that much in the bigger picture. But with the second data set, you've got almost double, well it is double, the DT50 value because you log transformed the data. So when we use weighted data, we always run it unweighted first. And this helps the discussion as we can show what the impact has been by weighting the data. So it's always important to run it without it. So this is the kind of last set of rules we're going to cover, and then we'll have a Q&A session on this, because I'm looking around. And so I'll have a little Q&A just on the data handling, just to make sure everyone's on the page before I go to optimization. So many studies where you see a lot of degradation, you'll come across values less than the LOD or the LOQ. So if you have any values that are between the LOQ and the LOD, you would set this to the measured value. However, if, especially in older studies, it's reported as less than the LOQ, you would take the midpoint. So that you would add the LOD and LOQ together and divide by 2. When you come to less than LOD values, we only use the first data point after less than LOD. So if you can imagine, this is the blue line is the LOD value. If we were to model, maybe there's 5 or 6 data points here. If we were to model this, we would be modeling a straight line where degradation did not occur. So your K value would be 0 because it's a straight line. This would force any kinetic model into a biphasic behavior, because after this point, it's a straight line, and you're ignoring what happens in the majority of the degradation. So after the first less than LOD, you would use this first sample, and this is set to 0.5 of the LOD, and you would omit any samples after that time. The exception to the rule is that if you had a data point, theoretically after 100 days, that was above the LOQ, so the red line, if that occurred, you would include these less than LOD values. Does that make sense? So use some examples to put this in context. I'll use an LQ of 5 and an LOD of 1, just for simplicity. So we have so this first, these are very simplistic numbers. You go 100 to 80 to 50 to 5. We don't really care about this. At time 20, you go to less than LOD. At time 25, it's less than LOD. What you would do for this data set is assign this to be 0.5 of the LOD and omit this value, because nothing after this time point that we know of increases above the LOQ. For example, you have 150. In this one again, we get to this value is less than the LOQ, but still greater than the LOD. So we would include this value. This value is less than LOD, so it would be assigned to 0.5 of the LOD value, but it goes above 6. So for example, if we had maybe 2 or 3 LODs between this, because it went above the LOQ, we would include all data sets between this time point and this time point, even if they were all less than LOD. That put it in a bit more context. There is an example in the focus kinetic guidance, and I'll get the page open, so at coffee break you can have a look. But it is one of the more complicated bits to get used to. So for metabolites, I've already said that we will, I didn't see that on there. There's also the formation and the decline phase, plateau phase and the decline phase. So the rules that I've just explained for parents, you would also apply to the metabolites. So after the peak onwards, the same rules as parent apply. You would set your time 0 sample to 0 mass, and your less than LOD values are set to 0.5. However, in terms of the formation, you would only include the first less than LOD value that occurs prior to the first attack, so you're greater than LOD. So you can't quite see it, but so this would be set to 0. This value here would be omitted because it's not the first less than LOD value prior to the first attack, but you would include this value here, this time point. And you would include all these time points, and then you come to your LOD rules again here, and this is the first less than LOD value, so you would include it. If there were 3 or 4 more less than LOD values, you would not include these unless the concentrations increase to be above the LOQ. Then you would include them. Right, so that's data handling. It's very factual. Are we okay to move on to optimization? And hopefully it might make sense of what I was saying about the initial concentration being fixed or constrained. Yeah. Okay, so I've explained how you would treat the raw data to get it ready to put into your kinetic model. What I'm going to explain now is how you or a software package will figure out what's the correct parameter to consider within your kinetic assessment. So with regards to kinetic analysis, we're looking to minimize the deviation between the predicted and the measured concentrations by altering your kinetic parameters. So that's your K values, your initial concentration, G, and PV. The software packages we use today are going to use the least squares method, or called RSS. And this looks to minimize the deviation, the residuals, so this pink lines, to be as small as they can mathematically be. So in the optimization procedure, you will tell the model some initial guesses for your parameters. So your initial concentration, if it's SFO, and your K value. The model will calculate the curve with the data you have told it. So it might not be a great fit, because these are just your starting guesses. And the model will calculate the RSS value, which is how it's going to measure the goodness of fit. The model will then modify the parameter and repeat the process. It will then calculate the curve and calculate the RSS. And it will repeatedly do this until certain conditions are met. And ideally, these conditions are when you have a perfect match between the calculated curve and your measured data. So the software will use automatic optimization. And it will stop when either the convergence or termination criteria are met. The convergence criteria are met when the comparison between the RSS for the actual, so your current run, and the previous run is found to be within a set minimum difference. And this is going to be, it's pre-populated in the software, but you can edit it if you wish. So what the model is saying here, you have not seen a significant difference between your current run and the last run. So we're not seeing a real improvement when looking to reduce the RSS value. The other option is that the model will stop after a certain amount of runs. So even if it can't find a good fit, it will stop because the software will run a certain number of simulations. Again, you can edit this manually. So if you got termination criteria met as a result, it could be that you need to update your model to do more runs, but also it could be that it doesn't fit, and there is no possible solution. But be careful, just because the model has found a parameter match, it doesn't necessarily mean you find the most appropriate fit, or the fit that has been found is appropriate for use. And there's a couple of issues that we come across when we're optimizing that you need to be aware of. So James has already mentioned non-uniqueness. So this is where the optimization is unlikely to give a unique answer. And it can be largely influenced by the combination of your starting initial guesses. And it often occurs when two parameters are strongly correlated. So as you adjust one parameter, the other will adjust itself to reduce identical DT50 values, DT90 values, and comparable RSS values. Another example is where biphasic fits. They're using a biphasic model, but the data is truly single first order data. In that case, you'll also find you can, for example, alpha and beta, such as this example, can be very different from each other, and you still end up with the same results. So these two graphs, you can see alpha and beta, so 957 and 10,000. And this one, alpha is 6,696, and beta 70,030. They're very different parameter values. However, the residual sum of squares are comparable, and your DT50 and DT90 are identical. So to check whether we've got non-uniqueness, we always do kinetic analysis where we start with two different starting values. So you don't run it twice. That is a minimum to see if you've got non-uniqueness. And it's especially critical when you have a large number of parameters. So for SFO, you might start with a little bit less compared to hockey stick or DFOP because you've got more parameters to optimize. And using incorrect initial guesses can lead to finding false minima. So when the model thinks it's found the lowest RSS, and I think this is probably the easiest way to imagine it. Think of a mountain range. if you start at the top of this hill and you walk down the ridge here, the model will see the RSS decreasing, which it wants it to see. But after this point, if you start coming back up again, the RSS will increase. So the model will think that it's found the minimum RSS because you've told it to start at this point and it's went down, and then when it starts to go up, it knows the RSS, the lowest value, is here. However, if you started further down, maybe up here, and you went down this hill, you would find a lower RSS value. So the starting, but whether your starting parameter will influence where the software will start in this mountain range. So if you have 2 or 3 different parameter guesses in your simulation, you should limit the potential of finding this false minima. But remember, just because the convergent criteria is met doesn't mean that the fits are acceptable to Focus Kinetics. You need to go through the Focus Kinetic guidance on the goodness of fits. And equally, it could have found the best available fit, and it's still not be good visually. So there's, a few of you said you're involved in pesticides, so you may have seen discussion on OLS, or ordinary least square regression, or IRLS, quite a lot. So I'll point out now, OLS in older documents can be called NLLS, non-linear least squares. I'm Scottish, S's are not great for me. So the original Focus guidance recommends use of unweighted fits for parent and metabolite as a first step. So OLS regression assumes that the error variance for the parent and metabolites are the same. However, we know that in some instances, the error variance for parent and metabolites, especially when the concentrations of metabolites is sufficiently lower, but the error associated from the parent and the metabolite is different. So what this can lead to is that if you use OLS for parent and metabolites, which considers the same error variance, you could end up with the metabolite parameters failing the t-test simply because the error variance is that of the parent. And so it would make it more difficult to get an acceptable t-test. So when James was talking about, don't just simply look at 0.05 ticker across, you might want to consider which process you've used, IRLS or OLS for your metabolites. You should get the same answers from parent. So in 2014, the Focus guidance was updated and a clarification was included to indicate that OLS or IRLS will be used, is acceptable for use. But it's worth noting when you're looking at your results to be aware of which one you're using, especially when you're looking at metabolites. So some key Focus recommendations, and you have to know this is the last slide, so you can get your coffee soon. So you should avoid over-parameterization. A robust optimization is only possible if the number of observations is larger than the number of model parameters. So your 2, 3, 4, 4. You should always, and I think this is key, always evaluate the visual fit. The decline curve is created through your optimization procedures. If the calculated curve differs from the measured value, it could be that you need to optimize your parameters further. It could be that you need to fix your parameter as the model's trying to run, it's found an RSS with a different combination, but it's not sensible to do so. So you may restrict your initial concentration. If your initial concentration was 95%, but through the optimization procedures, the lowest RSS value required an initial concentration of 50%, you might say, well, that's not sensible to do, that's by DT50, in theory. You may tell the model to restrict the optimization to only consider optimization for the parent between 100 and 80% as an example. So it can't go too low or too high. Another example will come this afternoon's formation fraction. So it's worth keeping in mind. You can do something with that. But what a formation fraction is will become clear this afternoon. But remember, no matter what you do with your optimization, it doesn't guarantee a good fit. It could be that you've just selected the wrong kinetic model. So one of the key things, we came across some problems with false minima and also non-uniqueness. So it's really important that when you do your kinetic analysis, you do it a few times with different starting values. This will help you identify non-uniqueness and also make sure that you truly have found the best combination of parameters. So we talked about common sense a lot, and when you get your resulting DT50, it's worth checking that it actually makes sense. Has the model calculated a DT50 that you would expect to see given the data set you have? Okay. So it's got here, and I think probably leave this until the Metabolite workshop has been done. But if you have a really complex metabolic pathway, you can use something called stepwise fitting. That makes it simpler for the model to optimize. But I'm not going to explain it now, because I think without knowing the background to metabolites, it won't make much sense. So when James comes to metabolites, he'll repeat this again, but it's worth keeping in mind, stepwise process will be discussed. Also be aware of the differences that you can get from different models. So they are coded differently. Different models will allow a different number of metabolites, different types of processes. So some will allow for back transfer, some won't. And just keep in mind, OLS and IRS may give you different statistical results, especially for your metabolites. So quite a very quick run through of two chapters that are worth reading in focused kinetic guidance. At this stage, any questions about anything we've said in this first quite long, I think everyone's waiting for coffee session?
Coffee time.
Yeah.